Okay, we came to the point that we started to discuss about norms, and we finished talking about different type of vector norms. And as the course was mainly focusing on the matrices, so we need to know how to find the norm of a matrix. So today's topic is a matrix norm. Okay, we want to talk about matrix norm. The operation which is from n by n to what is the expectation? Is from Rn by n to in the vector form it goes from Rn to R. In matrix it is what do you think? Do you understand what is this? Like what's it for the normal vector norm we had from Rn to R? What does this mean?
There's a vector and then it's...
The domain is a column vector with the size n, and the codomain is a scalar. Right? This is the dimensionality n, this is the dimensionality 1. So this is what it meant. It means that you give a vector and you are getting a scalar. So here, the domain is an n by n matrix. What is the output? R, because the norm of a matrix, you remember, for the Euclidean norms is a number. It's a number. Is matrix norm if it satisfies the following three properties. So similar to the vector norm, which we had three properties to be satisfied, we have the same thing in the matrix form. Matrix norm. The first one. Norm of a matrix. Do you remember what was the first property for the vector? Vector norm?
To be greater than 0.
The norm is greater or equal than 0. The similar thing, the norm is greater than or equal to 0 for any A belonging to R n by n. And norm A is actually 0 if and only if A is 0. Second one, norm of alpha A. This is absolute of A, absolute of alpha multiplied by norm of A for any A belonging to R n by n, and for any alpha belonging to R. And what was the third one? What was the third one in the vector norm? Very famous.
Triangle.
Yeah. Triangle inequality, which was saying that the norm of A plus B is less than equal to the norm of A plus the norm of B. Of course, for any A and B belonging to R n by n. Now, Frobenius norm, or known as matrix Euclidean. Norm is defined by is equal to, I write several things in green, but the final terms that I write is what you need to know. Now, the Frobenius norm is actually the addition of all the elements of the matrix squared, and then the results will be under S square root. We call it the matrix Euclidean norm. It is at the same time equal to the addition of all the singular values of a matrix squared, and the result of this summation will be under S square root, which is the trace of A transpose A under S square root, or the trace of A transpose under S square root. You can finish writing, then I have a question regarding to what I have written in Greek. Okay, can I ask my question? Can you tell me that what are the numbers, the limits for I and j here?
M and N.
No, you tell me, it starts from what to what for each of them? What is the starting value? What is the ending value for I? What is the starting value and what is the ending value for j? Right?
0 to M and 0 to N.
What is 0? First element is 1. 1 to m and 1 to n.
Sorry, 0, 1.
Yeah.
1, 1.
Okay, Hassan, what about the second one? What are the limits for k? Rana?
Are they like in a diagonal matrix, or are the singular values placed in a diagonal matrix?
Well, I mean, these are the sigmas from the singular value decomposition, of course. So what is the starting and what's the ending point?
Starts from 1.
Okay.
Should be n minus k.
M minus K?
Sorry. N, because we're talking
N.
about the rank.
N.
Yes, n.
Why N? Why not M?
Because we're talking about columns, so the number of columns.
If we have this matrix, I mean, these are not zeros, like elements.
Yeah.
Which is a 2 by 4. Looking at 4 is the rank.
No.
Okay, so you are right. It has to be 2 up to rank. Let's say R, where R is rank of A.
Yes.
But if we write it something else, it is also okay. Do you know what we can write? Minimum of M and N. But why do we prefer to write R? What is rank? How can I understand what is rank from singular value decomposition?
The number of non-zero.
Zero singular values. If I put minimum of M and N, and if rank is less than the minimum of M and N, it means that there are a lot of zeros that I'm adding, which I don't need to do it. That's why we keep it as R, because rank can be less than the minimum of M and N. Can you give me an example, Ike? How can I have a matrix whose rank is less than the size, the number of rows and columns? Example is this. You're mistaking the exam. I mean, it never leaves you. And then this is 1 by n by 1, and this is 1 by n. Right? This is an n by n matrix whose rank is 1, which is less than n, right? So we keep it as R. However, if you write it minimum of m and n, it's also okay, because then you start to add a series of zeros. So not n only. So let's continue by having further definitions of norms. If you remember, when we were talking about the norm of a vector, we had this general norm, P norm. And from P norm, we got like norm 1, norm 2, norm infinity, and so on. So let's define the P norm. Remember, this is the Frobenius norm, F norm, and now we want to talk about P norm. So the matrix P norm P norms are defined by, and this is a definition actually which we have seen it at the beginning of the semester in the first chapter when we were talking about norm 2, but in a more general form. It is the maximum of norm of xp not equal to 0 of norm of ax p norm of ax divided by P norm of X. And in some books we have different notation. It is the maximum of norm of AX, the P norm of AX. What should be the condition here? What type of condition do I have to write that the P norm can be calculated by this? Under what condition this formula will become this?
X equals 0. I want.
When the P norm of X is 1. And I don't need to write this condition. Why?
You're not dividing
It's
anymore.
already 1.
Because it's already 1, so it cannot be 0. Right? Now, so this is the general P norms, and as we remember from the vector norms, there are actually 3 of the norms which are very, very well known for us. Norm 1, norm infinity, and norm 2. So let's see how we can calculate it. Famous computable cases are, so we understand that some of the P norms are not really easy to calculate. First one, the maximum column sum norm. There is one of the norms which is called the maximum of column sum norm. In other words, we are adding all the columns of the matrix and we are picking up the maximum one. And this norm is nothing but the norm 1 of a matrix. So norm 1 of a matrix is the maximum J belonging to N with the underline. I mean it is all the columns of the matrix. It's all the columns of the matrix. Right. So what we do for each column, we are adding all the elements, adding all the absolute value of all the elements, and then we see that which one has the maximum result, and that result is the norm 1 of our matrix. This is called the maximum column sum also. So norm 1 of a matrix is called the maximum column sum. The second one is the maximum row sum norm, and it is nothing but which norm? Norm infinity. Maximum I belonging to M underline, which means it's all rows of the summation J from 1 to N of A I J. And the spectral norm, which is norm 2. Of A, and this is maximum eigenvalue of A transpose A, which is the maximum eigenvalue of A transpose, half of the eigenvalues, which is, we know it, this is actually sigma 1 of A transpose A. I'm sorry, sigma 1 of A. So these things that I have written in parentheses in small means that this means that you have to calculate A transpose and then find the half of its maximum eigenvalue, which we know that this is actually the biggest eigenvalue of A that we have. So it's very easy, very useful, very, very useful thing in many computer science application. Calculation of the second norm of A. And you can always find the maximum singular value. And then here it is. Apparently, the application is more useful when you need to calculate the biggest singular value, rather than going to the singular value decomposition, which is very expensive. You can calculate this by knowing what is the norm 2 of A. And you can always calculate norm 2 of A through its, by maximizing the gain of A by using the actual p-norm formula. And let's have one small note. But the note is like a question I want you to answer. What is the norm 2 of A plus? You want to answer this?
No.
Okay.
Why do we have A transpose A and A transpose? Wouldn't it be the same thing as A? Where
No.
you calculate the...
No. Because what happens, A transpose A and A transpose are symmetric. I mean, they are square matrices, right? And when you want to calculate the singular value, eigenvalues, as we will see in the next chapter, and as we already know, it is the S squared of the sigmas.
So can't we calculate the eigenvalues without doing A times A?
Oh, you can. No. You didn't get it. For A, you can calculate eigenvalues. For B, another matrix, we can calculate eigenvalues. For A, S square, you can find another eigenvalues. For A transpose, you can find another eigenvalues. Well, let's say I1, Y1, lambda 1, lambda 2, lambda 3, lambda 4, they're different. But I'm telling you that the norm 2, if you want to find the norm 2 of A, you have to find the maximum eigenvalue of A transpose A. This is a formula. If you find this, which you can find a number, it is not the norm 2. It is not the norm 2. It's like this. 5 to power 3, what is this? This is 5 multiplied by 5 multiplied by 5. Can I add 5 3 times? You can add it. Will it be 5 to power 3? No. In other words, can you calculate the lambda of only A? Yes, you can calculate it, but this is not that.
So, is this orthogonal, the A,
No, we didn't put any condition.
but it's a square matrix?
A transpose A definitely is a square matrix. A transpose is definitely a square matrix. This one is n by n. This one is m by n. Why? Because A transpose will be n by m, A is m by n. Here, A is n by m, and is m by n, and A transpose is n by m.
Because there's a case when it's the same thing, it's equal to the, so calculating the eigenvalues of A transpose is the same thing as calculating the eigenvalues of A. So that's what.
But there might be a case that A transpose is equal to A. You might come up with a matrix where A is equal to A transpose. And it can be a matrix like this, a matrix which is a linear transformation and it is symmetric.
Basically, that's identity matrix, that's all. Thank you.
When can we have a linear transformation? When the matrix P is linear transformation, P square is equal to P. Right? This was, we had it, the theorem for that one. And then if you come with the matrix with an example, I don't want to strongly say that it's an only identity matrix, it can be another matrix. However, this is the formula, and I still don't understand what is your question. It is like that P norm of A is this, and then you ask that, can I add A by another matrix? You can, but will it be this? No. The definition says that if you want to find the second norm of A, you have to find the eigenvalue of A transpose A, the maximum eigenvalue of A transpose A, and the square root it. But still, I did not understand what was your question.
It's okay.
But what was your question?
It's because I wanted to know why we are using A transpose A and A transpose when it could possibly be just A.
Well, it's three operations. This or this or this. Which one do you have to pick? Which one do you pick, in general, if you want to pick?
Maximum singular value.
This one?
Yes.
And I'm telling you that you have picked the most expensive approach. Because in order to calculate this, you have to find the U. You have to find the V. It's not that you can get the sigma 1.
So it's not easy to calculate the eigenvalues as well.
These ones calculations are easier because you are talking about lots of linear equations which you have to solve them.
And that's not easy either.
If you say calculation of this one is not easy, the calculation of this one is hell.
This can be calculated very easily.
How do you calculate this one very easily? Can you please tell me what is the U, sigma, and V of this matrix?
I mean, if I have MATLAB.
Oh, if you have MATLAB, this one, comment is EIG.
Yeah.
You can tick tock and see with high probability this comment will work slightly faster than this comment. I mean, like 1 millisecond, 1.2 milliseconds. But there is another thing in MATLAB, if you love MATLAB, you can write norm to A and it directly gives you the norm 2. You don't need to use SVD and then go find the biggest value, it directly gives you that value. And as I told you, mostly the application is this. You want to find this one, because SVD is very, very expensive operation. I just calculate the norm 2, which is very easy because of this. And I just substitute it in here. For instance, in the singular value equalization, instead of going down and calculate SVD, because we only care about the biggest one, I don't go to SVD at all. I just find the norm of an image, and I say, here it is. I mean, you are comparing it very unfair for this one use pen and paper, this one use your fastest computer and MATLAB. It is like, is a bike fast or a Ferrari? And I can tell you that an old bike is faster if you remove all the tires of Ferrari. Yeah, you see. Okay, now, you ask question, it's my turn. It's revenge. I can you tell us, what is this? The norm 2 of A plus. Laura is also thinking because he may also help. Then Dana, then Hassan. You might want to see was it the first chapter of the book or second chapter of the book where we had the same formula. But instead of A plus, I was talking about A inverse.
Reciprocal.
Reciprocal of what?
Norm A2.
1 over?
The norm A2.
Okay, don't write anything. Let's first write what you suggest and see which one is correct. Any objection? Dana? Any objection? No, he's my friend, of course. Objection, Law?
No objection, but yeah.
Dana, still?
No.
No objection. Ike?
I can't come up with any other things. So.
Okay, so let's see if it is correct or not first. Norm 2 will gives us we have to look at the maximum eigenvalue. Square root of maximum eigenvalue, which means that the biggest singular value. It doesn't matter whatever you have here, what you put in here, maximum eigenvalue. Now, if this is a maximum eigenvalue, 1 over maximum eigenvalue, it gives us the smallest possible number, so it's wrong because this should be the maximum eigenvalue in here. So this result is not correct. Why? Because this one already is the maximum eigenvalue, and 1 over maximum eigenvalue definitely will give us a small number.
Okay, so it's 1 over the smallest singular.
Okay, very good. It's 1 over the smallest singular value. Can you tell me that what is the smallest singular value?
It's the smallest non-zero singular.
Can you tell me that what it is?
Sigma K.
Sigma
K.
R.
R.
Right. 1 over sigma R of A. Why? Because the sigma R is the smallest non-zero singular value, which 1 over that one is the biggest, which is the biggest. And of course, by R is the rank of A. R is the rank of A. The eschaton P norms is defined by norm of S and P of A is sigma 1 to the power of P plus sigma R to the power of P to the power 1 over P. And again, what is R? What is R?
Right.
Right. Two very important notes. There's gotten two norms. Is Frobenius norm, and the Scotten infinity norm is norm 2. I mean, there are lots of different norms. I have not seen like the application of any that I am writing now, but you might see in your field of research. The mixed norms can be defined as norm of A, P and Q is the maximum of norm Q of X not 0 of norm P norm of AX divided by Q norm of X.